Okay, this is lesson 1.1, the first of our actual lessons in data management, and it is on, this whole unit is on probabilities. So it's an introduction to probabilities, as you should know at this point, and so we're going to look at what a simple probability is, and in particular we're going to look at experimental probabilities as our jumping off point. So just a question to sort of set the stage here. How do you know if seatbelts in your car are going to work in a collision if you've never been in a collision? Hopefully none of you have ever been in a collision, and I mean, we assume that seatbelts are going to work. How do we know that that's the case, right? Well, we don't, obviously, but what has happened is that data has been collected. So people have looked at collisions throughout history, of the history of automobiles, and they've looked at whether people are wearing seatbelts and whether they're not, how they fared. Even, I'm not sure if I'm supposed to interpret this question as, do I know whether seatbelts work as in protect you, or whether just your particular seatbelt will work. I'm assuming it means will they work as in protect you if you're wearing it. So they compare people who wear seatbelts to people who don't wear seatbelts and see how they fare, and they've definitely seen that people do better if they wear a seatbelt than if they don't. So that would be what's happened. So data has been collected and then it's been interpreted, and those we can think of that as a kind of experimental probability. It's a kind of experimental probability. Obviously, no one has actually done an experiment where they cause people to be in a crash and get the results. So it's not an experiment in that case, but it's experimental as in it's based on reality. It's based on something being done. In this case, people getting into car crashes provided the experiment that data could then be collected from. And again, then they saw, okay, if you're wearing a seatbelt, you had maybe a 90% probability of survival compared to maybe 50% for people who weren't wearing seatbelts. And so it's based on real world. Now, what's an acceptable percentage of success for seatbelts in car? Well, I mean, fill in your own. I'd like to think that 100% probability every time I buckle up that I'm protecting myself. So anyway, probability involves making predictions about situations or events. A probability experiment is a specific action that has at least two possible outcomes. And that's what I was just talking about above. So so we could think of this this previous example as a probability experiment that has two outcomes, survival or death. And what's the probability that either one of those is going to happen based on real-life events? The probability of a certain outcome represents how likely it is to occur, which we represent with a number on the probability scale. So all probabilities have to lie within a set of values. So that set of values, if we don't, before we put numbers on it, let's just think about it in terms of describing it in words. At the far left, let's say it's impossible that happen. So whatever we're measuring can't happen. So if we're talking about rain today, if it's impossible that it's going to rain today, that's at one end. If it's 100%, well, I'm already throwing numbers in there, but if it's a guaranteed sure thing that it's going to happen, that would be the other end of the scale. So we'll say that that's certain to happen. And then we have things that are in between. So we've got maybe in the middle, we've got a fair chance of something happening. We've got unlikely down at this end. And we've got likely up at that end. But again, these are just words, right? And it's good. Often words are what we want to help us put things into perspective. But if we then put numbers along with those things, well, if something's impossible, the probability of it happening is 0%. Whereas if it's a sure thing, the probability of it happening is 100%. We can't really go above 100%. not when we're talking about probability anyway, and we can't go into negatives either, so it's got to fall between that range. So then we could just break up the scale and say 50-50 for a fair chance. If it's unlikely, somewhere between 0 and 50, and if it is likely, somewhere between 50 and 100%. That's as a percent. Or we could do as a decimal. We know that we can switch percents to decimals by dividing by 100. So as a decimal, that would be 0, 0.25, 0.5, 0.75, and 1.0. So all probabilities have to fall between 0 and 100% or 0 to 1 as a decimal. Now, I've already talked a little bit about experimental probability. This is probability based on experimental trials. Sometimes it's called statistical probability or empirical probability, but the main thing is it's based on trials. In fact, I'm going to underline the word trials because that implies we have to actually do something to get experimental probability. And again, when I say we have to do something, I don't mean we necessarily have to do the experiment. Nature may provide it for us, but something has happened that we're then measuring. Experimental probability of an event A is determined by the formula P at A is equal to N at A over N at T. So it's the probability of event A, that's P at A. N at A is the number of successes that's N at A. And N at T is the number of trials. So what do we mean by a success? Well, success simply means what's being measured, okay? So don't get hung up on the idea of success necessarily being a good thing, because sometimes it's not. Subjectively, if someone's measuring how the death rate in car crashes, and if it's framed that way, a success might actually be a death. Now, obviously, no one would consider that a success in the common sense of the word, but I'm just trying to point out that when we use number of successes for experimental probability, we simply mean the number of times that what we're measuring turns up, to take away that subjective spin on it. So let's take a look at an example. Determine the experimental probability of rolling a 4 on a standard die. What is it? Standard die rolled blank times. I guess there's supposed to be a number 12 in there because that's how many spaces are in the table here. So you can't see me roll a die. I'm just going to go for a simulator here, and so I'm just going to roll this die on the simulator, and every time and I'm going to record my results. So I'll record them on a piece of paper, and then I'll transfer them to the table in a second. So first roll, I got a 6. Second, 5. 3. 3 again. 6. 2. Halfway through without a 4 yet. 7 gives me 1. 8th roll gives me 3. 9th gives me a 6. Oh, there's a 4 on the 10th roll. 3. And my last roll, the 12th roll, is a 5. Okay, so as I said, I just jotted those numbers down. Now I'll just transfer them into my table here. 6, 5, 3, 3, 6, 2, 1, 3, 6, 4, 3, 5. So those are my individual rolls. Right? So determine the experimental probability. So event A is rolling a 4. So the probability of A is the number of successes. Well, how many successes did I get? I got 1 success on the 10th roll out of the total number of trials, which was 12. So my experimental probability would be 1 over 12, which I could express as a decimal by doing 1 divided by 12. 0.083 repeating. Will this probability always be the same if the experiment's performed again? I would think not. I don't expect to always get 1 out of 12. And that's because probability involves a certain amount of randomness. So that's not to say that I can't predict that, what I think is likely to be the number of 4s that come up, but I certainly can never say I'm going to get exactly 1 4. I guarantee I'm going to get 2 or 3 or 0 or 12 or whatever. I can just sort of think logically about things and predict it. But one of the ways that I can think logically about it is if we do this experiment over and over and then start to see what outcomes we get over repeated trials, that's one way of making predictions about the future. So that's experimental probability. Now, just to change gears for a second to subjective probability, that is a probability of an event determined by intuition or experience, not necessarily by math, okay? So maybe you can call that a gut feeling. At best, it's an estimate. For example, the Weather Network predicts that on any given day in April, there's a 40% chance of rain. How many days should it rain in April? Well, actually, there is some math involved in this, but let me just give it a slight skew on that for subjective probability. I'm looking at the window right now, and I see clouds in the sky, and I'm not using advanced techniques for predicting rain like the Weather Network would, but there's some clouds there, and without knowing anything else, I'd say maybe there's a 50% chance of rain in the next hour. But it's my gut feeling. It's based on my previous experience. I know that when the sky is cloudy, it's rainy. Right now is the month of October. I know that in October, often we get a lot of rainy days. So a lot of things come together, and some of them I might not even be aware of, but I can get a feeling for it. Anyway, once I've got that probability, I can use it to make predictions. The Weather Network predicts that on any given day in April, there's a 40% chance of rain. How many days of rain should it rain in April? Okay, well, we want 40%. We would expect, if it's 40% per day, we'd expect, 40% chance on one day, 40% chance on another. We'd expect overall we're going to have it rain 40% of the days. And there's 30 days in April. So 40% of 30 days would be, change that 40% to a decimal, because whenever we're working with percents or with probabilities, we need to have them as a decimal or a fraction. Percents are good for understanding, for helping us visualize it, but we need to change it to a decimal whenever we do math calculations. So 0.4 times 30 is 12. We'd expect it to rain about 12 days in April. Now, let's get back to the experimental probability, though. A mystery circular spinner containing 4 spaces, each with a different color, is spun. The following results occur. We got green 14 times, red 12, blue, blue 8 times. So we want to determine the experimental probability of each event and fill in the results into the table. So I want to find, say, the probability of getting green based on these experimental outcomes. So if we consider, well, it even tells us up here that the favorable outcomes, this column in the middle is the favorable outcomes. It's N of A, so we got 14 green. We need to know what N of T is, though, don't we? We need to know the total number of experiments. Well, that's just, if we add them all up, 14 plus 12 plus 6 plus 8, that ends up equaling 40. So the experimental probability, P of A, is going to equal N of A, 14, over N of T, which is 40. And I could reduce that, or I could change it to a decimal. That reduces to 7 over 20, or 3.5 over 10. So let's do that as a decimal, 0.35. That's what 14 over 40 would reduce to. And red, I don't have a red. Let's see, get a red highlighter so I can do that. All right, red, that's going to be 12 over 40, which is going to reduce to 3 over 10, or 0.3. Yellow is 6 over 40. That's going to reduce to 3 over 20, or 1.5 out of 10. So it'd be 0.15. And blue, yes. Blue is 8 over 40, which equals 0.2. Now, the first thing that I just want to point out is that probabilities, if we add up all the different outcomes of things, it's either got to be green or red or yellow or blue. If those are the only options, then our probability should add up to 100%. So if I was to add 0.35 plus 0.3, I get 0.65. Add 0.15 to that, I get 0.8. And add 0.2 to that, I get 1.0, or 100%, because that covers all my options. It's got to be one of them. So another way of looking at it is the probability of getting green or red or yellow or blue is 100%, since that's all I have to work with. Draw what the spinner could look like based on your data. Well, just as a rough sketch, I would want the spinner, if I was based on this on the data, I would want the percentage, so if I got, say, green as 0.35 as a decimal, I know that's about 35%. I would want about 35% of the spinner to be green. So about 35% would probably be this section here, right? So there's green. Let's even color it in. So there's green, 35%. And red was 30%. So maybe I'll just do that over on this side. It's easiest to estimate there. So not quite as big as green, but still fairly large. And let's see, yellow was 15%. Well, I know that 15 plus 35 adds up to 50, so I can probably just extend this line straight down. That would be our 15%. And then what's left is the 20%, which would add to the red to give 50 as well. That's my blue. So maybe this spinner looks exactly like this. All right? So, okay, no problem. Why might this not be the actual spinner? Well, again, this is just based on experimental values. They could change. So we did 40 spins. They could change with every group of 40 spins. So in other words, this is one group of 40 spins. I'm thinking of that as one whole experiment with 40 trials. What if I did another group of 40 spins with 40 trials? Chances are it wouldn't work out exactly the same. And in fact, maybe what my spinner looks like might even look more like this. Let's see. Maybe it's just completely equal, because just because they turned out to have more green and red than yellow and blue doesn't mean that they had more space on the wheel. And that's the randomness of probability again. So we have to consider that anytime we are dealing with probability, as we're going to see as we go through this course. So here's another possible way the spinner could look. We don't know. No one showed us the spinner. We're just sort of working backwards to think about what it might look like.